Yeah. So, good evening. Myself Harish. I'm from Mysore, Mohali. I will be taking the problem solving sessions for this course, Introduction to Abstract Group Theory. So, let me just share my screen. Okay. So, we will start by discussing some practice uh, assignment problems. If you have any doubt at any stage, you can let me know. Let me just reshare it. There is some issue. Okay. So I'm just pasting the practice assignment question and then we will start discussing it. If you have doubt from the lecture notes, then also you can ask. Otherwise, we will be discussing the some practice assignment problems and some more problems. Yes. I hope the question is visible. If you have any query, then you can stop me anytime and discuss that. Okay. So this is from practice assignment 1. Uh, so we need to select all true statements that are true. So I won't be discussing the first two parts because they are also there in the uh, main assignment. So I will start by the third. So these two are there in, I should write part of graded assignment. So I won't be discussing these. So we can start from the third one. So it says if G is an abelian group with the identity, sorry, if G is an abelian group with identity element E, and X and Y are two elements inside that group with the property that X square is equal to Y square equal to I identity, then the product XY also satisfy this property that XY square is also identity. So we need to see if this statement is true or false. So let me so it's this statement is true. So let me just prove it for you. Uh, I can just assign some numbers to them. 1, 2, 3, 4, 5, and 6. So we are going to discuss the third one. I think this some sidebar is coming. Uh, yeah. Mm, so we need to check what this XY square is. So this is simply xy times xy, and since g is abelian, so I can take this x here. I can just swap this y and x. This is because g is abelian, and thus it becomes x square dot y square, and it's already given that x square is identity and y square is identity, so this will be identity again. Okay, so this one is, third statement is true. Okay, so any doubt in that? Okay, so I assume there is no doubt. Okay, so now fourth one is already done in the class, that every group has unique identity element. Maybe I can just resolve it for you. Uh, so assume that E1 and E2 are two identity elements of the group G. Uh, then since E1 is an identity, uh, we have, so you using that E1 is an identity, we will get E1 group composition with E2. So E2 group composition with E1 is same as E1 group composition with E2, and that is E2, right? Because E1 is an identity. So if it is composed with E2, either sides, we are going to get E2 again. And since E2 is an identity, of G, we can write, we have, again, we will be using now that E2 is an identity. So E1 composed with E2 is same as E2 composed with E1, and that is going to be E1 again, because now E2 is going playing the role of identity element. So when it is applied to uh, uh, so now E2 is playing the role of identity. So when it is applying to E1, we are going to get E1 again. And now from 1 and 2, so from 1 and 2, what we get, so these two are equal. Thus, the identity element is always unique. Okay. Yes. Okay. So now let's see the fifth part. So this is also true. Fifth part says that that G be a group with identity element E if X belongs to G is satisfies X raised to 10 is identity, then X inverse also satisfies the same. So we are given that x raised to 10 is identity, and we are supposed to show x inverse also satisfies this property. So how to do that? Uh, so x is inside so since x belongs to G, x inverse also belongs to G, right? And x raised to 10, because which is just x, 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 x 10 times. This also belongs to G, and which implies x minus 10 also belongs to G, because uh, so this is nothing but so this is same as writing x inverse power 10 or x 10 inverse. Why is it so? You may require a bit checking, so maybe mm, I can leave that part. But this part is clear, right? X inverse belongs to G. Now what you do, uh, since x10 is equal to identity, even this part you won't require. You just operate as x inverse uh, 10 times and you will get the answer, both sides, of course. So let me just share. Oh, it just went. Yeah. So right. So what I want to say that x in 10 is equal to identity. Now you apply x inverse both sides. So what you will get, x10 x inverse is identity times x inverse. So this is you can add the powers, and here it will be just identity time x inverse is x inverse. So this will implies x9 is x inverse. Similarly, apply x inverse uh, again. How many times? Maybe 9 more times. You will get x9 times x inverse dot 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 x inverse, and here you have x inverse and x inverse, right? So here it is also 9 times, and then you will get this is identity, and this is x10, and uh, which is, or I must say, this is x inverse raised to 10. This is what we are supposed to show, that x inverse raised to 10 is also identity. This part is clear, right? Because we will be subtracting inverse this -1 9 times. So this will be x raised to 0. I can just write here that this is x raised to 0, which is nothing but identity. And hence you get x inverse raised to 10 is identity. Okay. Now let's come to the sixth question. Says let G be a group with identity element E and x belongs to G. Suppose that x raised to 6 is identity and x raised to k is non-identity for any positive integer k less than 6, then G has at least 6 elements. So why is it true? So this is true because uh, so identity x, x square, x cube, x4, x5 are all distinct elements in G. So what is the justification? So since x is not equal, x raised to k is not equal to identity for any k less than 6, this is already given. Instead of writing since, I can simply write it is given. Uh, it is given that so so identity cannot be equal to the other 5 elements. Also, if xi equal to xj for some ij belongs to this 1, 2, 3, 4, 5 index, this index set, then what will happen? Then this will imply xi, and we can just simply multiply xj inverse, which is uh, this is identity, and this is xi x minus j. So this you can check that xj inverse is nothing but x minus j. And this is identity, and it will imply xi minus j is identity. And here we are assuming that I is greater than j. So j less than I. Yeah. For some ij belongs to this and uh, j greater than, sorry, j less than I. ठीक है. Yeah. So this is again something inside 1 to 5 because I is greater than j and j is already inside 1 to 5. Uh, Now since j is less than 5, I and uh, ij are both inside 1 to 5, this number cannot exceed 5 and it is positive as well. So this will again belong to 1 to 5. So thus x raised to I minus j equal to identity contradicts uh, what's so this contradicts uh, the assumption that xk is not identity for k belongs to 1 to 5, right? There it was written that k less than 6, which is same as saying, uh, oh, it should be not equal to, yeah. Now, here I can simply say, let assume, if possible, just changing some language. So, this is a contradiction. Thus, this xi cannot be equal to xj for any ij between 1 to 5. And this implies that 1x, x square, and this x cube, x4, x5 are all distinct elements. Okay. So I hope it's clear. If not, you can stop me anytime and ask your doubts. This finishes the first problem in the practice assignment. So these two statements are also true. Okay, so let me just paste assignment. Uh, just paste question, problem 2. Um, Here is problem 2 from the practice assignment. So from next class onwards, whenever we have a this problem solving section, we can solve the assignments for which the last date is already gone. So I won't be helping you directly in solving the uh, assignments, because those are graded ones. But for those which are already for whose the assignment for whose deadline is already gone, that we can discuss after the deadline. And you can ask me your doubts also for the ongoing assignments, but I won't be giving the complete solutions. So let's see this. So it says let G be a group with identity, and there are given four elements from the group A, B, C, D, satisfying some relations. So it is saying A cube B square C4 D minus 2 is identity, and A4 is not equal to identity. Also C square is not identity. So which of the following is or are correct? So yeah. So first statement says that A square, B square, C square, and D square is A inverse D4. So those relations which you can directly derive from this identity, you only those statements are supposed to be correct, because you don't know what are the other relations present in this group. So only one relation is given, this, and also A4 is not equal to A, or C square is not equal to E. So this implies A cube is not equal to identity and C square is not equal to identity is given. So using this equation only, you need to solve these four statements. So in first one, it's saying A square, B square, C square, D square is A inverse D4. So uh, since we have A cube, B square, C4, D minus 2 is identity. So this will imply, so I will multiply A inverse both sides from left. So A inverse A cube B square C4 D minus 2 is A inverse E, which implies, so A inverse will reduce this power 3 by 1. So this will be A square B square C4 D minus 2 is A minus 1. Now multiply D4 both sides. So this is C D minus 2 D4 is A inverse D4. This will implies A square B square C4 D square is A inverse D4. So again, let me just give some numbering. 1, 2, 3, and 4. So this one is correct. A square B square C4 D square is A inverse D4. So this implies second is correct. And in first, there is a slight change. So instead of C4 here, we are having C square. So can these two statements be simultaneously true? Let us just quickly see that also. Then first we have C square in place of C4. If first is also correct, then so they both have the same RHS. So LHS should be same. So this will imply A square B square C4 D square is A square B square C square D square. And then cancellation also you can apply directly. So A square, because in group left and right cancellation always holds. That is also been discussed in the class. So we'll just simply cancel at these one by one. Again, do the cancellation, and this will implies C4 is C square, and which is, you can write C square, and then C square identity. So again, cancel C square. You will get C square is identity, but it is given that it is not identity. So it's a contradiction, right? So first one is not correct. Now, what about the third one? So we have B square C4 is equal to D square. Hmm. So if third is correct, then uh, or let's first try to come up with the LHS part from whatever equation we are given, and then we will see if the equality is there. So we are given B square C4 in the LHS, and in the relation we have A cube B square C4 D minus 2 is identity. Since A cube B square C4 D minus 2 is identity, therefore A cube B square C4. Again, simply I will take this here is equal to D square, and if B square C4 is equal to D square, then we have A this is equal to B square C4. Again, use the cancellation rule, and this will imply A cube is identity, which is again a contradiction. So third one is also not correct. What about the fourth one? A cube B square is D square C minus 2. So since A cube B square C4 D minus 2 is identity, therefore A cube B square C4. So I'm taking D square there is D square. This will implies A cube B square D square C minus 4. Just I'm taking this here, and here it is given D square C minus 2. So if A cube B square is D square C minus 2, then A cube B square, oh, then D square C minus 4 is D square C minus 2, which will imply C minus 4 is C minus 2, and then taking C square C4 here, identity is C minus 2 C4, which implies identity is equal to C square, again a contradiction. So the fourth part is also wrong. So thus the second part is correct, and all three are wrong. Okay, so any doubt till now? You can see this solution uh, for some seconds, and if any doubt is there, then let me know. Otherwise, we will move to the next one. Okay. So I assume there is no doubt. So let me come to the next question. This is going to be an interesting one. Here it is. So it says, it asks whether for an abelian group G, the subgroup H, which contains all uh, elements G with G square to be identity, is a subgroup of is a group itself. And if it is a group, then as it's a subset of G, it will be a subgroup of G. So whether this statement is true or false, so let us show that. So first we need to show whether uh, the set is closed under the group operation. Means the group operation is a binary operation on H or not. So first is uh, H closed under the group operation of G. So this is the first question. Now we will answer this. So this has already been answered if you observe the previous questions. So we have already shown that if, yeah. So see, third part of the first question, that if G is an abelian group with identity E and XY are two elements satisfying this property that X square, Y square is identity, then XY will also satisfy this. Thus, if X and Y is inside H, then their product XY will also be inside H. So this is by the third part of the first question. By question 1, part third. Uh, or I should write for clarity. By question 1's part third, uh, if XY belongs to G, then, sorry, uh, belongs to H, then their product X dot Y also belongs to H. So this is been proved earlier, so I am not going to prove it again. Second is identity of G. What is the identity of, identity of H? Now, since H is a subset of G, so whatever element satisfies the identity relations for uh, G, the same element will also satisfy the identity relations for H, since H subset of G, therefore, for all x belongs to H, x dot E is E dot x, and that is E. And further, so we need to show that this identity element is actually inside H, right? Further, E square is E dot E, which is again E. This implies identity belongs to H. So identity is there. Third one is the inverse. But I can simply write here that if X belongs to H, then X square is identity. And we have already seen that this implies X square X minus 2 is E times X minus 2, which is simply identity X minus 2. And this is same as X inverse square. So X inverse is already inside H. Right? This inverse is inside is with respect to the group, but as the group is having a group and H have the same identity, so the same inverse will work for H as well. And we have shown that this X inverse is also inside H. Fourth, since H is a subset of G, therefore H inherits. Or in simple words, I can say, therefore H also satisfies. So satisfies the associativity property. Associativity property. And since H is satisfying all these relations, all these properties, H is closed under the group operation. Identity of H is there. For each element in H, X inverse is also there. And H is also satisfying this associative property. So this implies, so this is for subset, not subgroup. H is a group. And in particular, it is a subgroup of G. Okay. So I hope this is clear. So let me just write some more questions for you. So we can maybe discuss one or two more examples which are not part of the assignment. So as an example of the group, so I can say some more problems. So first is let GL2R be the set of all 2 by 2 matrices with entries, with real entries, then first problem is GL2R a group with respect to matrix addition. So is it a group? Uh, so you can see that it will satisfy all the properties, but the basic property is missing. So the solution uh, let O2 be, I should not write O2. For the moment, let's write just O. Let O be the matrix 0, 0, 0, 0. Then for any matrix A belongs to GL2R, A plus, this plus is matrix addition. This is same as 0 plus A, and that is A. Because you are adding, so you can simply see this. It's a trivial observation. And this will be just A plus 0, B plus 0, C plus 0, D plus 0, and again you will get A, B, C. So it's a trivial observation that this uh, matrix satisfies the role of the identity for this matrix addition. Now, what about inverse? So this is 0 is the, or better notation is this, I think. This would be a good notation. Okay. So 0 is the additive identity in GL2R. Oh, but here the problem is this matrix 0 is not inside GL2R, right? Because we are talking about the invertible matrices and this is not invertible, right? And since identity is unique, therefore GL2R does not contain additive identity. In fact, it's not a binary operation. So you can see the second question is this: is addition of matrices a binary operation on GL2R? So if you can answer this second question, then of course the first one is also done. But just to explain you some more stuffs, I have solved the first problem in a different way. That's an answer to the second question also implies uh, also gives the answer to the first question. So is it a additional is addition a binary operation? So the answer is no, uh, because no, because if A belongs to GL2R, then minus A also belongs to GL2R, right? Because if A has determinant 0, then minus A will also have determinant 0, and this will implies A instead of implies, but A plus this minus of A is A minus A, which is 0, and 0 matrix, which is not inside GL2R that we have already seen, right? So this is not even a binary operation. Okay. Now, what about the multiplication? Is the multiplication of matrices a binary operation on GL2R? So now we need to check whether the two matrices are closed under the matrix multiplication inside GL2R. So let's solve that. So let A equal to A, B, C, D belongs to GL2R, and or maybe I think we don't even require this. We can simply uh, take A and B belongs to GL2R. We're not going. We don't need to go element wise inside this matrix. The whole matrix is enough. So it is inside GL2R. Then determinant of A is non-zero, and also determinant of B is non-zero, right? Uh, Also determinant of AB. So determinant of product is product of determinants, right? I hope you know this relation, this property of determinant. So this is non-zero, this is non-zero. So this implies that this is also non-zero. And since this is non-zero and uh, we know that a matrix is invertible if and only if the determinant is non-zero. So this implies AB belongs to GL2R. Okay, so it's closed under the matrix multiplication, or matrix multiplication is a binary operation on GL2R. Now, another thing is GL2R a group with respect to the matrix multiplication? With respect to the matrix multiplication. So, just think about it for a moment. So we have already shown that it's a binary operation. So solution. So binary operation part is done. Now what about identity? Should not write one here. So we know that for I2 to be just the identity element, A times I2 is I2 times A, and that is again A for all A belongs to GL2R. And in fact, it happens that this is true for all matrices. So no need to be elements of GL2R. And I2 is also inside GL2R, right? Because its determinant is 1, which is non-zero. Thus, GL2R contains identity element. Of course, all this is happening with respect to matrix multiplication. Right? Now, what about inverse? So, if uh, A belongs to GL2R, then determinant of A is non-zero and determinant of A inverse is what? 0 and I should write. This implies determinant of A inverse, which is 1 upon uh, now since let me just write it again. Since determinant of A inverse is just 1 upon determinant of A, and how this is coming? This is coming since determinant of I2 is determinant of A times A inverse, right? And we know that determinant of product of two matrices is product of their determinants. This is determinant of A inverse, and this is of course equal to 1, and this implies determinant of A inverse is 1 upon determinant of A, right? Of course, we need A to be invertible. That means the determinant is non-zero. So this relation is okay. We can divide by determinant of A. There is no harm in that. So now this is non-zero. So 1 upon determinant of A is also non-zero. And this implies A inverse is inside GL2R. So GL2R is also closed under taking inverse. Now what about the associativity? Also, for any matrices A, B, C in GL2R, or not just GS2R, we can just say for any also for any 2 cross 2 matrices, or I think square matrices is enough. For any square matrices A, B, C, A composed with BC is same as A composed with B, then C. So it's always associative, and hence GL2R is a group with respect to matrix multiplication. Okay. Okay, then. Now, let us discuss some example, or maybe we can try to draw one composition table or multiplication table. We have not done that, so let's try to uh, do it for S3, which clears all your doubt for S3. Mm. So question 2, draw composition table, or in at some places this is also known as multiplication table, but composition table is uh, uh, a good notation. So let's stick to that. For the group S3. Okay. So since the cycle notation of elements in S3 is not been yet discussed in class, so I will be defining elements in a very uh, naive manner. So uh, S3 contains, so let uh, or so there are so many ways to write to represent S3. We will stick to this way. So uh, let F1 be the map which says which maps 1 to 1, 2 to 2, 3 to 3, and F2 be the map which map 1 to 2, 2 to 1, and 3 to 3. Also F3 be the map sending the index 1 to 3, fixing 2 and 3 to 1. F4 be the one that fixes 1 and changes 2 and 3. F5 be the one which maps 1 to 2, 2 to 3, 3 to 1, and F6 be the map that maps 1 to 3, 2 to 1, and 3 to 2. Okay, so then S3 is just set of all bijections, right? Set of all bijections on, in fact, it's a group. So group of all bijections on a set of size 3, right? So we can say in a vague manner because it's almost same. Later we will see the concept of isomorphism of groups. So then you will realize that it is okay to write S3 as just a collection of these elements F1, F2, F3, F4, F5, and F6. Now we want to obtain the composition table for S3. So composition table for S3. So what is the composition table? It's a table with number of uh, rows equal to the number of columns, and that is same as the number of elements in the group. So there are 6 elements. So we need to draw six rows. Of course, there will be one uh, row that will describe the columns, and there will be one column that will describe the rows, that is separate. 4, 5, and 6. Okay. So let me uh, just give me a second. Uh,
Recording in progress.
oh, yeah. So let me just draw this line again. This is looking very funny. So yeah. So there are six elements. So let me just put them in these F1, F2, F3, F4, F5, F6, F1, F2, F3, F4, F5, and F6. So you need to obtain the composition table. Okay. So clearly F1 composed with Fi is mm, same as Fi composed with F1, and that is Fi again for all I belongs to 1 to 5, right? Because Fi is just the identity map. So this will be F1, F2, F3, F4, F5, F6, and this will also be uh, F2, F3, F4, F5, F6, right? Now, just to explain, this entry will denote, so this is IJ entry, so this will denote F2 times F6, not F6 times F2. Okay. And similarly, this will be denote. Okay. This will be denoting F6 times F2. Okay. So that is just for convention. So that you are not confused that from which side we are operating. So now, what is F2 times F2? So F2 is the element which maps 1 to 2. So we are applying F2 over F2. So 1 maps to 2. Then where 2 is mapped, so 2 is again mapped to 1. So uh, F2 times F2 will map 1 to 1, right? So maybe I can just show here. So what is F2 times F2? So this will be sending 1 to 1 and same 2 to 2 and then 3 to 3. So this is in fact equal to F1, right? Because F1 is also doing the same thing. Now, what is F2 times F3? F2 composed with F3, right? So first we need to compose, first we need to see where F3 maps the elements and then apply F2 over it. So F3 maps 1 to 3 and where 3 is mapped under F2, this is again at the same place. So 1 is mapped to 3, 1 is mapped to 3 and where 2 is mapped under F3. So F3 maps just try to see this is 1 3 and this is 1 2. So 2 here is just fixed, 2 going to 2, but here 2 is going to 1. So 2 will go to 1 as a whole output. So 2 will go to 1. And since we know that the group is closed uh, under the product, so it has to be a bijection. Thus, 3 should map to 2. So this is your F6, I guess. Yeah. 1 going to 3, 2 going to 1, and 3 going to 2. So this is uh, F6. Now whether so here I will write F6. What about F2 compose F4? Maybe I can just split this space in half. Yes. So where this F2 compose F4 will map the element. So F4 is sending the element to 1 to 1 and then F2 is sending 1 to 2. So 1 will map to 2, 2 will map to 3, and 3 will map to 1 as a whole, right? So it will be just F5. So 1 going to 3, 2, sorry, 1 going to 2, 2 going to 3, and 3 going to 1. So this is F5. Right, so here it comes F5. Now what about F2 compose F5? F2 compose F5 will be uh, so F5 is sending 1 to 2, F2 is sending 2 to 1, so 1 will be mapped to 1, and then 2 is going to 3, 3 is going to 3, so it is 2 going to 3, and 3 going to 1, and 1 going to 2. So it will be just F4. So this is 1 going to 1, 2 going to 3, and 3 going to 2. So this is F4, which is interchanging 1 and 2 and 3. Okay. So one more I will. So now again, see, we are uh, in group. So for group, so here comes a trick. Uh, uh, See, for any I, if Fi, Fj, you are multiplying, and uh, if you are intending to obtain these two products with uh, j not equal to k, then these products cannot be same if all these are distinct, because otherwise you will apply uh, this and you will get Fj equal to Fk. So which is not the case. So here you should get F2 composed with F6 should be something that we have not obtained, right? So F2 composed F6 should be someone which we have not obtained yet. So this is going to be F3, right? Directly one can write. No need to check. Now, what is F3 compose F2? So I will be doing this and writing the solution directly. If you have any other answer, then you can let me know. Okay. So I won't be like writing the entire, I won't be doing the entire calculation here, because otherwise it will be very boring. 5, 1, 2, 3, and F6, 1, 3, 2. So next we need to find uh, the entries in this row. So first is what is first thing to obtain is what is F3 compose F2, right? So F3 compose F2 is just give me a second. So 1, 3, and 1, 2, 1, 2, 1, 3, 3, 1, 2. So this will be, you can note that down that this is the one which sends uh, 1 to 1, 2 to 3, and 3 to, sorry, 1 to 2, 2 to 3, and 3 to 1. So this is your F5IS, right? Yeah. So this is your F5. What about F3 composed with F3? So you can check that this will be just F1 because it is just changing two elements, two indices. So again, if you do the same thing, then it will, the final answer is just F1, which is fixing everything, right? So here also you can see that this will be F1 because it is also F4, and F4 is also just changing two indices. Okay. So now what is F3 compose F4? F3 compose F4. So this will be 2 going to 3, 3 going to 2, 2 going to 1, 3 going to 2, 2 going to, and 1 going to 3. So this will be 1 going to 3, 3 2 going to 1, 3 going to 2. So this is nothing but F6, right? So F3 compose F4 is F6. And what is F3 times F5? I'm going to do this. Let me just write here. F3 compose with F5 will map 1 to 2, 2 to 1, and 3 to 3. So this is F2. So similarly, we can obtain other also. Let me quickly finish this. So we have not obtained F4 here. So this one will be F4. And same trick we can apply column wise also. So this one will be obtained easily, this last row. So we just need to calculate for these remaining, some of the remaining entries. So F4 composed F2, F4 compose F2 is, oh, yeah. So F2 maps 1 to 2, uh, and then F4 maps 2 to 3. So this will be, just a second, 2, 3, 1, 2. 1 will map to 3, 2 will map to, oh sorry, 2 will map to 1, and 3 will map to 2. So this is F6. And then F4 compose F3. Uh, this will map uh, 1 to 2, 2 to 3, and 3 to 1. So this will be F5. Okay. Now we need to calculate this one also. Remaining one will be this. So let me just write what is F4 times F5. F4 times F5 is mapping 1, 2, 3, 2, 3, 2 will be fixed, and 3 will be mapped to 1. So this is fixed. Three. Okay, so this is F3, right? So it will come F3, and what is remaining? F1, F2, right? So last one is filled like that. So only one, these many entries we require, and then we will use the trick that all entries in the row and column should be distinct. Maybe I can mention here F4 times F6 is F2, since all entries in a row must be. So let me just split this part of it. Must be distinct. Okay, same logic applies here. Okay. So now for F5 we need to check. So what is F5 composed with F2? So F2 maps 1 to 2, and uh, so F2 maps 1 to 2, and then F5 maps 2 to 3. So overall 1 will be mapped to 3. F2 maps 2 to 1, and in F5 1 is mapped to 2. So 2 will be fixed to 2, and in F2 fixes 3, and F5 maps 3 to 1. So this will be 3 going to 1. So this will be your F3. I hope so. F3, right? Now we can also fill this one. Why? Because, but we will do it later. First of all, let's find out what is F5 with F3. So F3 maps 1 to 3, and F5 maps 3 to 1. So 1 is fixed. F3 maps 2 to itself, and F5 maps 2 to 3. F3 maps 3 to 1, and F5 maps 1 to 2. So this will be like this, and this is F4. Okay, so here comes F4. What is F5 composed with F4? This will be so F4 maps 2 to 3, and F5 maps 3 to 1. So who will be mapped to 1? F4 maps 3 to, oh sorry, we should start from 1. So F4 fixes 1, but F5 maps it to 2, and then for 2, F4 maps 2 to 3, and then F5 maps it to 1, and then F4 maps 3 to 2, and then F5 sends 2 to 3. So this is F2. Okay, so this will be F2. Now what is F5 composed with itself? So F5 composed with itself will be, so F5 maps 1 to 2, and then 2 is mapped to 3. So 1 will be mapped to 3, then 2 will be mapped to 1, and 3 will be mapped to 2. So this is F6. Okay. Now using the same trick as before, what is remaining? F1. And F5 composed with, I should use this red separation, right? So this will be F1. Since entries in a column must be different, must be distinct, therefore F6 composed with Fi is obtained directly from the current table. Or instead of is, you can write can be obtained directly from the table. So how can we do that? So you simply see this. So in this column, what is remaining? F4, right? And in this column, what is remaining? F2. In this column, what is remaining? F3. In this column, what is remaining? F1. And in this column, what is remaining? F5. And you can check that here also everything is distinct. So overall, we are not having any mistake. As per this trick that everything should be distinct in a row or a column. So finally, so this automatically comes to be distinct. So there is a chance that we have done all calculations to be correct. Hmm. Okay. So that's it. We have got the composition table for uh, S3. Okay. Now, mm, maybe some more questions we can try. Find the inverse of 1, 2, 2, 1 in GL2R by using matrix multiplication. So we need not to apply direct trick because there is also a direct trick to do that, but we are supposed to get it through matrix multiplication. So how to do that? Solution. Let B to be the inverse of this element in GL2R. Then this element multiplied with this should give us identity, right? Which implies we just need to do the matrix multiplication. A plus 2b is 1 and 2a plus b is 0. C plus 2d is 0 and 2c plus d is 1. So if we solve this, then we will get, I can do more. Maybe I can first get rid of one variable and then put it in the equation to get the another. So from simply 1 minus 2 times second is gives you a minus 2a, oh sorry, 4a to be 1, which implies a is minus 1 by 3 from first. 2b is 1 plus 1 by 3, that is 4 by 3. Okay. And then if you put these values in second, then we have 2a, which is minus 2 by 3. There is some issue, I think. It's not satisfying second one. So we have committed some mistake. So 1 minus 2 times second, that is a minus 4a, and that is 0. So minus 3a is 1. So a is minus 1 by 3. So 2, oh, it should be from 1 to b is, it's correct, right? 2b is 1 plus 1 by 3, which is 4 by 3. So this will imply b is 2 by 3, right? And now these values will satisfy 1 because minus 2 by 3, sorry, minus 1 by 3 plus 4 by 3 is 1, correct? And minus 2 by 3 plus 2 by 3 is 0, that is also fine. Similarly, from first, from third and fourth. So see, these two are same as first and second. So you can see that if you replace B by C and D by A, then these equations are identical as that. So C will be 2 by 3 and D will be minus 1 by 3. So this implies B is equal to minus 1 by 3, 2 by 3, 2 by 3 and minus 1 by 3 is the inverse of what was the matrix 1 2 2 1, right? 1 2 2 1. You can also see from our usual trick that the determinant is 1 minus 4, that is minus 3, and then we need to interchange this, so this will remain same, and then we need to apply so from that trick also the same answer will come, right? Okay, so this will be the inverse. Maybe we can do some more question and then stop. So let's see this question. This is also an easy one. If an is equal to identity, uh, okay, I should write that G is a group, and so let G be a group and A belongs to G. Let N belongs to L be the smallest integer uh, with an equal to identity. Then for any m belongs to n, am equal to identity if and only if n divides m. So generally, this question is discussed after the definition of order of an element, but that is not yet discussed in the lecture. So I'm not defining what is an order of an element, but this question makes sense without knowing the definition also. So what it says that for any group, if A is inside that group and n with the smallest integer, such that a raised to n is identity, then whenever we have am equal to identity, then n must divides m. Also, the converse is true, that if n divides m, then am is identity. So let us first go in the forward direction, or maybe the other way, because other way is easier. So if n divides m, then there exists r belongs to n such that m is equal to n times r. Okay. And thus we will have am to be just a and r, and this is a n raised to r, which is identity raised to r, and then it is identity again. Okay, because any power raised to identity is identity. You are just multiplying identity r many times. So one part is done. Now what about the other part? So let am equal to e. Okay. Now since n is the smallest integer, with an equal to identity, uh, this will implies that m is of course greater than n, greater than equal to maybe, right? Because n is the smallest integer for which this holds. So by using or even let's not say so many theorems. So it's obvious that if m is greater than n, this will imply that there exists some Q and R, some natural numbers, such that M is equal to NQ plus R, and uh, R is between 0 to N minus 1. So this is basically you keep on dividing M uh, until you get a reminder that is strictly less than N. Okay, so this is just division algorithm. So now what you do, uh, this will uh, then you simply put this value of M in this equation. So then AM is simply A raised to NQ plus R, which is A NQ times AR. So we can just, this is addition in power, so we can just separate. And what is this? This is A N raised to Q times AR, right? But AN is already identity. So this is identity raised to Q times A raised to R. And that means this is identity. And identity times some element is again going to be that element, right? So what you have got, right? Okay. But this AM is already given to be identity, right? This will implies identity is equal to AR. Okay. Uh, Here there is some trick. And be the smallest positive I should write, right? Otherwise, one can say that 0 is also there. So smallest positive. So here also I should write positive. Okay. So identity is AR, where R is strictly less than N, right? Or I can say that R is inside N to this. So this implies R has to be 0 because N is the smallest positive integer, smallest positive integer with AN to be identity. So, and R is strictly less than N, so it cannot be positive. So it has to be 0. But we know that M is NQ plus R. So M is just NQ because R is 0. And that implies that N divides M. Okay. So now just to give some motivation. So this smallest positive integer for which AN is equal to identity, this is known as the order of the group, or order of an element. So I can just write it in star. So the smallest positive. So the solution has been ended here. I'm just giving you a new definition, which will of course come in later lectures, but it's a good opportunity to define it. So I'm just doing that. The smallest positive integer for an element A belongs to G such that an is equal to identity is called the is known as the order of A in G. Okay, so the smallest positive integer for an element A belongs to G such that an equal to smallest positive integer n, I should write uh, for an element A belongs to G such that an equal to identity is known as the order of that element inside G. And the above exercise can be rephrased as uh, whenever AM is equal to identity, then uh, order of that element must divides M. And the other way is also true, that if the order of an element is dividing some integer M, then AM is equal to identity. Okay. So I think with that, I will stop. If you have any doubt, then you can ask, or from the next session, we will try to solve the assignments whose deadline is gone. And also, if you have any queries in the lecture notes, then also you can ask. We will first discuss those queries and then solve some practice problems. And you can also contact me at this mail ID. Any queries? Write to this is Harish, Harish, Krishnani, Kish, Ni, then 11 @gmail.com. Okay. So are there any queries, any doubts, or any suggestions for the next sessions? If you want to discuss anything, then also you can tell me. Uh, if not, then we will stop. Okay. So if there are no questions, then I will stop sharing and bye bye. So I'm ending the meeting for all. Okay.
Thank you, sir.
Okay.